Having completed our discussion at the lower levels of healthcare infrastructure components, such as the servers and the desktops, we now start our lecture 3, where we now look at software-based components and various models of computing, data processing, and applications that are in use. Our learning objectives in this section are to first introduce concepts and models of client-server computing, and we take examples from internet services, which is where most client-server examples are found. We then take a specific internet service, the World Wide Web, and we make sure that we understand how it works and why it has been so successful in implementing a set of features that have ended up being so useful. And then we look at how applications and data processing models are used in writing applications, so that when we go back to our healthcare applications, we can understand the software components that are part of it and their implications on performance, reliability, and other such quality attributes. So in client-server computing, recall that we have 7 layers of networking that we talked about, of which the 7th layer happened to be what network people called application layer. Turns out that there is no single application layer. There are many applications in the application layer, and those can actually be layered as well. So the application layer in client-server computing world, we would say, comprises of many services. You can call them applications. Users may call them applications, and those applications are collections of programs and libraries. These network applications have 2 components: a client-side program, which we generally would call client, and a server-side program, which we would typically call a server. So in the picture that you see here, the clients are in blue, and there's a file server that's serving up files. So there's a program on the file server end serving the files. And the client-side desktops would have a client component. The server running on the server computer typically runs forever, waiting for a request to come in, and its job is to provide service to a resource that it's managing, for which the request comes in. So in our example of the file server, the resource that's being managed by the file server are the set of files that are stored on that server. And clients can make various kinds of requests. So the 4th point being, clients typically started by a user on a desktop computer will make a request to the server by sending a request message. And in the example, you see the request messages coming in. One client says, get me this file, and a parameter of that would be the name of the file. Client 2 says, I would like to rename a file. Here is the previous name, here's the new name. And client 3 would like to remove a specific file and provides the name. File server has a server program that is waiting on the requests coming in, and then it acts upon them. The server receives the request or set of requests, acts upon them, and returns a reply message to the client. And in this particular way, several messages may be exchanged. There may be different types of requests and different types of reply messages. And collectively, these message types, the sequences of message and a reply and a message and a reply, as well as flow of data across these messages together, implement a protocol, a service protocol, in this particular case the file server service. So in our example, client 1 had requested get me a file or get me the contents of a file with a name. File server is responding back, here are the file contents. Client 2 was trying to rename a file. File server comes back with an error message that it cannot find the file that's to be renamed. And client 3, which was removing a message, file server comes back with a positive acknowledgement saying that the file has been removed. Examples of client-server computing in internet world are many, because every service that's implemented on the internet is essentially a client-server program. The first example we saw earlier was the domain name service, in which there are servers running domain name server programs, and clients send a name and expect an IP address back, or they can also send an IP address and get a name back, and there are some other details, other items that can be queried. There are other examples of naming services that are quite popular on the internet. One of them is called Lightweight Directory Access Protocol, or LDAP. You can use a client-server based authentication, like you can have a client submit a user ID and a password to check against what the directory has stored, and directory can come back and say yes or no. The purpose of the directory, however, is more like a phone directory. One of the things it can model very well are people and various attributes associated with people, such as the phone numbers, email addresses, their privileges, their names, their titles, affiliations, and so on and so forth. The way the service would be implemented, that a client may come and specify search for a particular person, or having found the person, provide specific attribute values such as the phone numbers or email addresses. Next example is a file and print services. Network file service, NFS, is a very popular one. Windows implements a common internet file service, CIFS, and Apple actually uses something called AFP. All of them essentially do, as our example shows, provide files to the clients. Similarly, on the printing end of things, there's an IPP, Internet Printing Protocol, or LPR LPD, whereby a printer is sent a job and the service request is to print it with a positive acknowledgement. Remote access or access to systems, those are the applications or client-server programs that are terminal and file transfer services. The oldest service is Telnet, with which a client program can become a terminal of a server computer, and that's Telnet. FTP is for file transfer. Secure FTP is to do file transfer with encryption of the contents. Secure shell and secure copy, SSH, SCP, these are examples of secure remote access and secure copying of files again. Email that we all use every day are examples of client-server programs. When one email server forwards email to another email server, they use a protocol called Simple Mail Transfer Protocol, SMTP, and if that particular protocol uses encrypted payload or encrypted data, then it's called SMTPS. When we are on our Outlook client perhaps, or Thunderbird client, or Eudora client, and access a particular mail server, we may be using a protocol called Internet Mail Access Protocol, IMAP, and if it's encrypted, it's called IMAP-S. And these are examples of protocols used in email. To see email, you use IMAP. To exchange email between two mail servers, SMTP is used. And then of course the most popular one, the web, World Wide Web. The name of the protocol is Hypertext Transport Protocol, HTTP, and if it's encrypted it's called HTTPS. One additional point to note here is that each service, if you recall, may have a specific port associated with it. It's not that you cannot run server on different port numbers. You can. However, a set of ports are pre-assigned to some of the protocols, and that's where they would be usually likely to be found. So when we do telnet, the port number in use is port 23. FTP is port 21. Secure Shell is port 22. SMTP is port 25. You can sort of see they started assigning these protocol numbers from around 21, and these are one of the oldest protocols that are in internet. HTTP happens to be port 80. So we go in a little deeper into understanding what World Wide Web is about. Now, World Wide Web didn't happen one fine morning. It actually came out of many other client-server programs already in place, being used in different contexts throughout the internet. And this was the internet before the World Wide Web days. World Wide Web came out around 93, 94 when NCSA Mosaic first released the browser. Before that it was designed in Switzerland and CERN by Tim Berners-Lee. But its popularity started with NCSA Mosaic program. But prior to that, applications such as Gopher from University of Michigan, Waze as an application or a client-server program which was about library services and finding information essentially. Simple General Markup Language, SGML. Apple in its early Macintoshes was showing a lot of hyperlink-like activity. Click on a particular part of the document, it takes you to another part of the document or another document altogether. That would be hyperlinking. MIME as a protocol or a standard has been around with emails. Since emails typically send text messages from one end to the other end of the world, MIME is a way to encode non-textual data such as images, such as programs, which are binary data, and converts them into printable text as an encoding, and then has an attachment method to an ordinary email and then sends it over. Now that's a way of packaging that World Wide Web has used. Public and private key cryptography, which gave us the security components, and so on and so forth. So let's just look at the features of World Wide Web and see how each of those features provide a quality attribute that makes it so attractive, that World Wide Web is so popular. So the first thing is links. Links, or URL, which is Universal Resource Locator, basically provides a feature so that one can leverage independent publishers. For the first time with World Wide Web, you didn't need a dedicated publisher to publish information. You yourself could publish information, and then you could link what others have published to what you are writing using a simple link, which is essentially a URL to another web page. So by doing that, the functionality and the usefulness of that system of looking at one place but having a ready reference throughout the internet was obviously a very attractive and successful attribute. The next thing World Wide Web did was it had multimedia. It not only presented text, but it has simple ways of producing graphics, adding audio, video, creating forms, and instead of just one-dimensional text display, which is the way Waze was, W-A-I-S was, by adding multimedia capabilities, and part of the multimedia is that depending upon what the media was, appropriate application could be started. at the browser level to act upon that media also added tremendously to the functionality of the World Wide Web. The next thing was platform independent rendition. For the first time ever, you could write a program, a browser, once for Windows platform, once for Unix platform, and once for Macintosh platform. But as the data was being sent from the server to the browser, it's the same data that was being sent to the browsers. Browsers knew how to interpret it and show it on their respective desktop platform. So what comes from the server is platform independent, but when it gets to the platform, the local program, the client program, the browser knows what to do with it in that platform. And not only it was simple from the server end of things, but it was highly flexible at the client end of things, because if you wanted and you did not know how to deal with a particular multimedia file, you could give it to another program which would open it up. Then the data that was being sent was used using markup languages, and the HTML hypertext markup language and currently the XML extended markup language. They're all derived from what we have written above, which is simple graphical markup language, SGML. And the beauty of markup languages is it's an ASCII or Unicode, if you will. It's not a binary data. You can actually take a look at it and make sense out of it. In fact, there is a browser which sort of takes away all the markers, all the tags, and just shows you in text what that page is all about. And it's a very simple way to add bold, underline, tabulars, tables, paragraph breaks, etc. And that was a brilliant use of the simple graphic markup language by simplifying it to hypertext markup language. Then, as a programming environment, World Wide Web encouraged dynamic computing. We'll look at this more detail when we look at Common Gateway Interface, or CGI, which is at the server end. But on the client end, you could add something called JavaScripts, and you can create applets, servlets, and by that what you could do is you could start do computational, take input from the user, send it to the backend. Backend could do something intelligent with it because it has the CGI to start other programs. By doing this, one were then able to not only just see static pages, but now could actually interact with the backend as if they're entering data in a transactional system. Then important security concerns were addressed by using public and private key cryptography in very clever ways, using secure socket layer. 2 or 3 things got done. A, traffic could be encrypted, and B, both client and the server could, if required, authenticate to each other and therefore provide a modicum, or not modicum, a significant component of trust between the server and the client. And the entire rise of companies like VeriSign and GeoTrust, who are the certificate programs or certificate companies, comes directly from security being important on World Wide Web to do commerce. And only when the security was addressed properly, the electronic commerce or internet commerce took off. And it's a significant contribution of the World Wide Web to assure the business community that this medium can be used for commercial purposes. By adding MIME type plugin, they added extensibility. So if one were to be sending to the browser a particular type of file that the browser has no idea what to do with it, it would come in a MIME encoded format, and then referring to a particular table, the browser could choose, should I start this application program on the data that you have sent? And these functions continue to grow. People have continued to add since 1996 and 7, when in the last 15 years the World Wide Web has completely changed the face of internet and the computing that goes on the internet. a new service like web services have been added. You can check the bootel.com website which has great details and wonderful details about World Wide Web. So what exactly happens in the World Wide Web, which is the Hypertext Transport Protocol? It turns out that it actually uses a layered structure within the application layer to accomplish its tasks. At the simplest level, there's a browser, which is the client, and there's a web server, which is the server. And the browser is going to say to the web server, send me a file that I want to render onto my screen. Turns out that Hypertext Transport Protocol, if you look at the picture to the right, is nothing else but the Telnet protocol. And so you could say HTTP is a protocol or a layer that uses the Telnet. You can go onto your PCs and type the command that's on the beginning, that's on the top, which says telnet www.bootel.com, and then you have to give a port 80 with a space port 80. If you don't give space 80, then it uses the default well-known port of Telnet, which is port 23, and I'm quite sure that bootel.com does not open port 23 to the world. It opens the World Wide Web port, which is at 80. So if you just did Telnet directly to them, you won't get any response. But if you do Telnet to Bootel on port 80, the way we have typed in here, you will see the response that comes back, which says trying. Then it says connected to www.bootel.com. There's a message which is typical of Telnet, which says escape character is control right bracket. I don't advise you to actually click on that. And then next thing you're going to type is that line which says get space / space http / 1.0, and then you're going to hit enter twice. But before I go further, I want to point to you that when you look at the telnet command, notice that it's using a name, a DNS name. An actual communication at the network layer would require the IP address, because that's how the network layer communicates to the routers communicate to the next machines. So what had to happen when Telnet was invoked? Telnet first invoked another layer of DNS, domain name services, to whom it presented the name www.bootel.com. DNS services did not know what the IP address of this particular name was, but looking at bootel.com, it had an idea to ask another server somewhere in the world about bootel.com. So in other words, HTTP, which uses Telnet, Telnet then invokes DNS. DNS does client server. Telnet invokes DNS in a client server fashion. DNS invokes client server programs to go discover the IP address of bootel.com, returns that to Telnet, and then Telnet uses that IP address to connect to port 80. When you type get / etc. and put enter twice, and it sort of requires it twice, you will see a response. And that response has two parts to it. First of all, remember HTTP is a protocol. That means it has its own header and its own data. And what you see on the top of the response in italics is all about the data that Hypertext Transport Protocol cares about. When you run this, go to www.bootel.com on the browser, you will never see any of that. It is purely for the consumption of the browser, which is following the HTTP protocol, to understand what's being said. A lot of things are being said. It's talking about where the server type is, in this case Apache, date, etc. You can see things like cache control. Cache control says no store, no cache, must revalidate. All that basically says is client side should not keep a copy of it. It should always come back to the server to get the latest version. And towards the bottom it says content type text /HTML. By identifying that, it's basically saying to the browser that look, what follows after this is going to be an HTML document, and it'll be of the type text, which basically means it's going to be an ANSI or Unicode encoded thing. following which the angular bracket starts, and whenever angular bracket starts with HTML beginning, you know it's an HTML document, and the entire content of bootel.com comes in an HTML document just like that. And because it is done in HTML, which is a part of HTML, it is purely printable, and you can actually take a look at it. And so every time you go for the first time to any website, this kind of an exchange actually takes place. And when that HTML document comes to the browser's interpretation of that HTML document translates it into a screen with appropriate bolding and titling and spacing as requested by the HTML. And that in itself completes a set of message exchange and a client-server message exchange between browser and the web server. In World Wide Web, naming is done through Uniform Resource Locator, or URL. An example of a URL is http://www.bootel.com. And the various components on that particular URL happens to be, first it says what the protocol is. In other words, the browser is flexible enough to not just speak HTTP, but it can also speak FTP. It can also participate in an SMTP kind of communication because of the mail to protocol, and so it can be extended. I have seen some of the vendors who provide streaming media to create kind of protocol that's related to streaming media. We have also seen Microsoft creating with its Office communication systems for web-based meetings another protocol, perhaps SIP, which is used for communications. Then there's a name of the server itself. An example would be dbmi-columbia.edu. One could actually put an IP address. If the name is provided, then the browser will automatically use DNS to find the IP address. One could add an optional port number by following the name of the computer, name of the server, with a colon and the name of the port number. So one could run a web server program. It doesn't have to be on port 80. That's why many times you see them running on 8080, port 8080. And then when that happens, the browser by default will always pick up 80 unless you put colon 8080, in which case it will use that other port. And then typically after that there is a path. In this particular example of education, HIT program, HIT program.html brings up the health IT certification details from the www.dbmi-columbia.edu system. Now there are other possible protocols, as we talked about, FTP, etc. And places like FTP, the interpretation of what path actually means would change. So if you would try to do ftp://ftp.columbia.edu/kermit, you will find that it takes you to a directory called kermit, and there's a bunch of files there that if you want you can just drag them to your desktop, and it will complete that activity using the file transfer protocol. The World Wide Web also added the CGI program, CGI interface, that was the part of how to make it dynamic. And this is the way it really works. You have the browser on the left hand side, and you can request to the web server to have a static page, which is essentially a form. So let's say a form is sitting in browser side, and a user fills in the form and hits submit. Then the form elements will go from browser to the web server. Web server, looking at the form elements, would determine that it cannot do anything with it. All it wants to do, all it has to do, is to start a program and deliver the form elements that have been passed to it to the program and let the program do whatever it wants to do. To start a program dynamically by passing the parameters, which are the form elements, is the CGI interface, gateway interface. And any program can be started by the web server using the CGI interface and passing in the parameters. Now that program, let's assume that it's interacting with the database, and all it wants to do is take the form elements, store them in the database, and give an acknowledgement back. So it could then interact with the database by SQL commands and store the data and pick up a result from the database and send it back by rendering an HTML document to the web server, which web server would then just simply forward it to the browser. And using this method, what happens is different kind of CGI programs can be written to do different kinds of things. They can be sufficiently flexible that they can themselves be client-server programmed to other systems, or they can actually access databases. They can do any kind of computation that the web server itself does not do. It is a great way to extend the functionality of the web server from just delivering static pages. Over past 10-15 years, this model has stayed true and has worked beautifully, but it is changing, and that's an important concept, that any system, even if it's very useful, will eventually change. And part of the change that's happening in the World Wide Web is that the old combination of web server with CGI programs are actually being replaced by environments, web application development environments. A typical environment on the open source world would be Apache with Tomcat server, which then within itself allows programs to be written. You could think of them as CGI programs, which are written in Java, and these in the language of Tomcat server, they would be what they call servlets. These servlets could communicate with the browsers. The browsers are becoming more partners in terms of exchanging information. In addition to just rendering simple HTML, if they received XML, they could actually do some computation as well. So in other words, nobody forces the client to just simply be a browser. It can then start to become different kind of a peer program. So SOAP protocol, which is object-oriented protocols that many companies are using now, and creating a partnership between the client end and the server end. And these SOAP protocols with XML data are giving rise to new kinds of interface to the web server, and they are typically called web services. Now, you don't have to use Apache Tomcat server. Microsoft .NET environment also has an example such as that. So those are the reasons, and that's how the World Wide Web works and has become so popular, because it has provided simplicity along with extensibility, flexibility, security, and great usability. Overall, all the great quality attributes we appreciate and we have learned that we need to appreciate, and World Wide Web provides that kind of functionality and provides those kinds of quality attributes. We now enter the world of distributed computing models. So when we talk about client-server, there are classes of different types of client-server programs. You've already seen some examples with World Wide Web and domain name services. Now we get to classify them in simple, straightforward ways. So we understand communication is the key. We understand that applications must exchange information, which is what gives rise to what we call distributed computing. Some computing happens at the client end, some computing happens at the server end. Properties of chosen communication methods do impact overall systems design and efficiency. You will see the models, you will understand what we mean by that. Models of distributed computing do help us understanding at a systemic and a higher level what is it that a vendor's application is doing, And if they are using one particular model, then we understand this has these implications regarding performance and availability. If they use another model, then we can argue that it has a different kind. But understanding the model helps us understand what the vendors are doing. Independent, the whole distributed computing discussion that we're going to have now will not talk about networks, will not talk about link layer, will not talk about physical layers. In fact, the beauty of understanding networks in layered structure is to modularize the various components and services in such a way that you can discuss everything at the application layer, which is what we are doing now regarding distributed computing model, but it is not interfered by what's happening at the lower layers. That's a great way of isolating and modularizing the understanding and clarifying how this distributed computing is going to work without confusing going to work. So the simplest computing model is what we used to know called master and slave relationship. An example would be you had a PC and there was a serial connection, and that serial connection, I'm talking of the old RS-232 serial connections, or a parallel connection which was a printer cable, and it connected to a printer. Printer does have a CPU of its own, but it's dedicated towards doing a great printing. But in a master-slave relationship, the master happens to be the PC to which this printer is connected, and all the PC is going to do is communicating with the serial line is send it the data and tell it to print. So typical dumb terminals, dumb printers, there would be no real graphics associated with those dumb terminals, typically unidirectional order. Master tells the slave do something and it gets done. And even today we have ICU devices which use RS-232 connections to the sensors that are connected to the patient, and when the data comes, the ICU devices just simply capture the data and store it. And pictorially, all you would see is a master with a slave and a slave, like terminals and printers. The simplest model that we have for client-server computing is the one that we already discussed. It's simple clients, 2 tiers. In the beginning, the idea was to be very efficient and useful. The graphics were not involved. Telnet, Secure Shell, FTP, these are all examples of great 2-tier client-server programs. And in the picture you can sort of see that a server offers mail, Secure Shell, and post office protocol, Apple print protocols, all in the simple way of 2-tier structure. Over time, we started getting desktops which were very powerful. They got a faster CPU, and as the operating system itself became graphical, both Macintosh and Windows became graphical user interfaces, people started adding a lot of logic regarding rendering that graphic, as well as do a lot of computation onto the client side. And that gave rise to not simple clients, but fat clients with a lot of logic into them, which they were using to do advanced graphics and advanced processing. So in an example like this, then you would see that desktop client gets data from the application server and actually then renders it, besides doing a lot of processing on it. So that would be a scenario in which the client became a fat client. The problems arising in this computing model are quite a few. People actually thought they can run production systems this way, and having run them for years, they found out that there are some problems that are extremely complicated in this model. An example would be the version problem. Because desktop client is significant amount of computational code that resides on it for both the rendering and for processing, as new upgrades come for that pieces of software, how do we push the new pieces of software to thousands and thousands of desktops throughout the institution? So changing the system was one big problem. The another problem was the client power problem. At some level, we would never have always the best possible desktops on every desk. So we would always have a mixture of 4 to 5-year-old computers to brand new computers. And so therefore, when an application is written with an assumption that a client has to be minimally this much powerful, we couldn't provide that across all desktops throughout the institution. The other components, we talked about the upgrade problems. The version problem also includes the fact that as underlying operating system changed, the change required us to upgrade all our clients to some other part, and that itself was also a big undertaking and a difficult problem. Many applications, as many fat clients got added, the desktop started to become bloated because each client server program wanted a fat client, and then they started to interfere with each other in terms of their requirements of the version of the softwares on the desktop end. And because there are thousands of desktops, each of these problems become very significant and time consuming. Because of the problems with the fat client, a new model was proposed and followed through, in which the idea was to make use of the graphics hardware that's on the desktop client and to just use it to render graphics, and that too graphics that has been first created and produced in an intermediate place, which in the picture is the Citrix server. So the way it works is that the application server in the back end provides data to an intermediate front-end machine, which is a Citrix server, where the logic is executed, the graphics is actually rendered, but the Citrix server then, which has no terminals, there's no monitor connected to those servers, then sends it over to the desktop client using a protocol called Citrix protocol, of course, and the desktop client simply takes the data that's sent by the Citrix protocol and renders it on the screen. By doing this, we first note that it becomes a three-tier structure. Citrix becomes a three-tier structure. If you use the same kind of concept between two Windows machine using Windows Remote Desktop Protocol, it would become a two-tier protocol. In olden times, there used to be a system called X Windows on the Unix, and it first started doing graphics rendering as a client-server program. One of the problems it faces was that it incurred huge networking costs, but the new Citrix clients and Citrix-based three-tier structures do not have the network problem. In addition, what you do in this particular scenario is that in the Citrix server, which is actually maybe a physical server or a set of physical servers, one actually starts to run virtual PCs on the Citrix servers, and whatever that's being rendered in the virtual PCs is sent over to the desktop client to just render the screen, and that is something that the desktop client can do very fast. So in today's world, these three-tier structures are very popular. Notice that you take care of the upgrade problem because all the upgrades have to happen only on the Citrix servers. So in terms of the numbers, if you would say that there are 5 application servers, and if they were desktop clients of the order of 5,000, you may at any time may have less than 50 Citrix servers which can handle the concurrent load that comes from 5,000 desktop clients. And it's much easier to upgrade and keep track of versions for 50 Citrix servers as opposed to 5,000 desktop clients. So that's why a three-tier computing model is quite popular model in today's world. So when we look at this is also called a thin client model, in which the graphics in the client is not really doing much logic. All it's doing is whatever has been rendered and putting it up on the screen. In the thin client model, the exchange of data is typically in the markup language. World Wide Web is an example of thin client model in which the browser gets an HTML document and just renders it. It does create a good uniformity across clients because the clients can be 3 to 4 years old or can be brand new, as long as they are asked to do something simple like either render an HTML page or just follow the Citrix protocol. Then they can actually do that even if they are older computers, and therefore uniformity is achieved. It's possible that the 3-tier structures can become 4-tier structures. So what we find nowadays is thin client access from all the workstations or the desktops. The intermediate application server, which is the Citrix server, we have fat client access to the application server. And it's possible that the application server, instead of just picking up the data from its disks, is actually communicating with the database server, which is a separate computer, and that gives rise to 4-tier structures in today's day. The new models that are starting up today, that are not just based entirely on graphics but also exchange of data, those are the web services model. And in case of HTML and HTTP World Wide Web, we exchange data using HTML. When you're using web services in which it's not about just graphics, then you're going to use XML, extended markup language, to exchange data. And standard protocols are used nowadays. Web services which are derived from HTTP, could be SOAP protocols, and those are the various ways today's computing models actually work. We now move on to applications, and in the applications we consider first the simplicity that there are 3 components to applications. One, there's a user interface where data are being reviewed, data are being added, as well as if it happens to be a device, then the device interface is what the user interface is about. The other side of the application is data being stored, because there are users who are looking at the data and manipulating the data, but that data is actually stored in the data store. An application itself gets the data and then processes it. And the various kinds of processing that are possible in today's applications are transactional processing, batch processing, and analytics. So we want to go deeper into this to see how in healthcare infrastructure these applications interact with each other in typically obviously client-server way, in either 2-tier or 3-tier structures, sometimes even 4-tier structures. And we want to get to a level where healthcare applications are being used to see how we move to even higher layer of application. So in an application entry and review of user interface, we know that we need today a real-time interface where users are going to be using the system in real-time mode. They have to be graphical in nature because that's just simply the expectation of this day and age. And it's going to be using some kind of a client-server communication. But note that the data that are being stored in the applications do not always come from the users. Many times they do, but also in healthcare they come from other applications. And when one application sends data to another application, it's typically independent background activity. That activity can be real-time or semi-real-time. That means a patient has been admitted by registration at 2 o'clock. If that admit registration message flows into other EMR and ancillary systems within next 5 minutes, we would call this system semi-real-time or batch. In this particular case, if it happens within 5 minutes, it will be a semi-real-time, and if it happens overnight, then it would be called batch. And typical standard of exchange of information at that level is going to be HL7, health level 7. We have several lectures associated with HL7 and all the standards. We have to remember that whenever we're looking at applications, 80% is the read. Users are looking to see what the data says, and about 20%. The data store end, we have various mechanisms of storing of a generic application. It could be storing things data in files. The files could be formatted or simple, or they're going to be databases, which are a collection of files with lots of indexes and indices and tools. Important part of data store is what kind of media we are storing it in, and its speed and its availability are all issues regarding planning a system which is going to use disk arrays and SANs and NAS, which is network attached storage, replication, all kinds of media activities based upon how useful is that data. The format of storage of data in databases, if they're relational or hierarchical, then there's a concept of learning how to create a schema. What are the various tables? What are the conditions on table values? And how are they modified and improved upon is all part of the data store activities. One has to watch out for the changing environment and should not be statically focused on what to solve for today. But in the rest of this lecture, we are going to go look at deeper how data are processed in applications. So the first model of data processing in applications is online transaction processing, or OLTP. OLTP is a kind of activity where the amount of processing is not very large. It is about capturing data from a user and storing it in the database. So it's lightweight processing, but it is very high volume during the work hours. During the work hours when the patients are coming in and the registration in every place are actually doing this online transaction processing to register that the patients come in. It is somewhat network intensive because all communication has to go over the network, and it is obviously dependent on the network. These applications are typically enterprise class applications, which is registration and scheduling at the highest level with the department systems. And these applications that are transaction processing, of course, always earn money because that represents some service that has been provided to the user. Contrast this with batch reporting, and I presume we don't call them offline reporting, but it could be. In the batch reporting functions, it is possible that your online transaction processing database, instead of being exercising it to create nightly reports, you would automate a replication of data from the database of our electronic medical record into a side SQL server database, where you can then run batch reporting without affecting the original system. So this is a decision you make only when you see and implement a system and you find that your batch processing is going to be very expensive proposition on the OLTP side. And if that is true and you have figured that out, then you figure out a way of copying the data out of your OLTP system into a smaller system where you can then run the batch reporting functions without bothering the OLTP system. When you're doing the batch reporting, it's a heavy database access because you're going to access patient information across on many patients. It is compute intensive because a lot of computational activities happen when the batch reporting happens. Typically towards the end of the month or end of the year, the volume of work goes up. Nowadays in the batch reporting, no one really prints the reports onto paper and distribute them. Instead, what you do is you take the printer output, and instead of putting on paper, you put it in a PDF file and you distribute using what else? Web-based solutions, whether they're wikis or otherwise, or SharePoints, where the reporting is distributed through web-based distribution. The trend, of course, is becoming more and more on the real-time reporting because you get better efficiencies and better systems and more business that way, and also to incorporate business intelligence as well as clinical analytics upfront, just in time, as opposed to waiting for a month later to actually execute. So for in our data processing, then here is an example of our order entry results review application at Columbia University Medical Center, New York Presbyterian Hospital, which uses Allscripts Sunrise XA order entry application. So let's look at the properties of this application. It is a Windows application. and has database servers. So it has application servers and database servers. The database servers are serving data from Microsoft SQL Server. What we don't tell you is that Microsoft SQL Server is working on top of a LAN on the disks, and those LAN isn't proper, the phrase is storage area network, SAN, and that SAN is replicated over multiple data centers using software that helps them to replicate that. So even though we're talking at a higher level, application level redundancy, even if we don't talk about it, we can assume that at lower layers there is additional redundancy available. So storage is on SAN, on the Allscripts end of things. The user interface it has is Windows graphical user interface. It also has an iPhone application. And the model of user interface on Windows is a spreadsheet model with cells having values, as well as the spreadsheet itself has tabs to go to different applications and look at different data. We offer Allscripts Sunrise XA order entry application using Citrix servers with a thin client environment. So because Citrix servers with desktop and application servers is already 3-tier, by adding the database server, this is a 4-tier application. The processing is online transaction processing. This is about what tests and procedures have been ordered for patients. And the batch reports that happen by taking a replica, the copy of the database, to the reporting database, and then the reporting is distributed through web distributions. Another example of data processing is again at Columbia University New York Presbyterian Hospital registration and billing system. This happens to be a Siemens product called Siemens Eagle registration system. The storage actually is on mainframe social storage area network. The operating system is IBM z/OS on IBM Z series mainframe, and we are working on vSAM files that are part of that system. We find that the user interfaces are quite archaic. They are still based upon old IBM 3090 terminals. However, nowadays we use more Telnet or TN3270, which is a client-server program, to sign on to these terminals, and one is developing a new web-based interface. This processing is still online transaction processing as people come in and get registered. Batch reports are generated to Windows servers to distribute it out through the web, and it understood how this component of the billing actually works. So when we take the data processing and we take transaction processing and the reporting, we get a picture in which we have a mainframe and we have a user sitting with a 3270 terminal and Telnet client, and the user uses 3270 terminal to access the data that is still sitting in z/OS. And if we needed be, user could actually Telnet into the application and get more information or help them. We then find that reporting, which is batch bills, which is a separate system that can be done in which the ancillary systems are sending the bills over file transfer protocol to Eagle, because it's also a charge system, and the reports it generates overnight are actually sent over to the Windows servers to be distributed over the web. So looking at this component, we see that the Windows server that serves the web actually has a web server, IIS, that is used by our user on the browser on the right hand side, and so user uses Telnet to go into the registration system and uses browser to look at the reports that come out of the registration system. Then within data processing, we come to the component which is called online analytic processing or decision support systems, OLAP and DSS. Here the view of the data is not as slow as batch, which is at night, but it is probably not as immediate as a transaction processing system as well. It is within semi-real time or intermediate term. So one is looking at the views hourly or daily, and you're looking at a multidimensional view of data that has come from multiple different applications, not just Eagle. And then the data are replicated to OLAP tools. They're typically business intelligence systems. So data comes from multiple sources. Time requirement is semi-real time. And what we get out of the system is alerting, which says if there is a concern clinically about a particular patient, that can be coded as part of Ordnance syntax, which is a way to write rules in the system. Then we can find that we can generate alerts out of the online processing. So when we look at the pictorial form of online analytic processing, we find that our Siemens Eagle system, which does the distribution, has the following analytics programs. There is an Allscripts TSI analytics programs in which we actually send data out to an outsourced environment where they run the analytics and we get reports. We also have created an internal environment of a web-based display of data on the business intelligence side that also gets data from Eagle. And then there is a system called StockCamp, a bolt-on system that is part of revenue cycle processes so that it can do better revenues coming out of Eagle. And it has a lot of proprietary knowledge on old accounts and Medicare payments, and therefore it works well in trying to recover. So when we look at the picture, we see that the Eagle has the analytics component in which data are sent to TSI, sent to StockCamp, sent to business intelligence services that are running on a Unix system, and other applications are also sending that kind of information to business intelligence services. So if we take this picture and merge it with our, we actually get this, in which on the left hand side are the OLTP components, and we have just newly added the analytic components. Note that every arrow out here is a client-server relationship. Well, what is it? Well, we find that from Eagle we verify charges or bills and eligibility, and in order to do that we are communicating with Blue Cross Blue Shield or Network Recovery Service so that our bills get paid, and other insurers. So that kind of communication can now be added to this picture to show the kind of data flow that actually occurs from the Siemens Eagle system into these other business to business. Then we notice that we actually have clinical data that are called ADT events, which is admit, discharge, or transfer events, that have to flow out of Eagle because it's the registration system into all the ancillary systems, lab, radiology, pharmacy, etc., because only then they get the latest information, so that when somebody calls in for a lab test, they already have that information pre-populated in their system. What else can we add to this picture? In our final slide here, we have added one last component to our data processing picture, where we are doing online transaction processing, reporting, analytics, B2B, movement of ADT data, and then finally we have added systemic data that comes from our credentialing database, which defines our providers such as physicians, nurse practitioners, physician assistants, which all have to be loaded into these systems for the billing purposes, as well as the definition of our users for the purposes of signing on into the systems. And these systems that maintain these databases have regular feeds, typically in the batch mode, sent over to our online transaction processing system, and that then adds to the complete picture of how data flows in and out of just the component that's dealing with registration and scheduling. This part is separate from our electronic medical records data flow, which has far more richer clinical data flow, and we're not going to show that picture because it is more complex and it cannot be drawn simplistically the way we have done it here. The goal here for us was to look at various processing of data models, data processing models, and by adding one component to other component, we show the relationships and how they're interdependent on each other, as well as in the layered structure how they use the lower level communication to actually exchange data. In our next lecture, we'll be talking of some specific healthcare middleware applications that are useful in all healthcare applications, and so we'll continue on to lecture 4.